Thanks to everybody for joining us with the first Fraser lecture. So I'm Sergey Foss, and I'm a colleague of Fraser. Actually, our doors are next to each other in our building for more than almost 7 years. And I'm very delighted to introduce Fraser. Fraser is a well-known specialist in the Stein-Chen method. And he wrote a number of interesting papers on that area. And what is funny that he never been to Novosibirsk, but he has a very close connection to Novosibirsk because his PhD supervisor Sergei Uchev was working at the Institute of Mathematics for many years. And now Sergei is a professor at the Leicester University in UK. And Fraser yes, finished his PhD studies with Sergei around 2009, as far as I remember. And then he had a postdoc position with Barbu in Zurich, and then he had a postdoc position at Bristol. And after some time, he joined us. He joined in Harriet-Watt University in 2013. So he will be with us, and he has kindly agreed to give a series of lectures, which will be given in a mixed format. So we agreed on the following: that due to this coronavirus influence, we cannot run our spring school, but we can do it in a much more different format. That Fraser has agreed to give 3 or 4 lectures. We will see how it will work. Today, next Thursday in 2 weeks, and so on, from 4 p.m. Novosibirsk time, 10 a.m. in UK. And this will be a 2-hour lecture. I think it's 2 hours. It means I think astronomical hours, not academic hours. 2 hours means 60 minutes, 120 minutes, with break 15 minutes. So it's about 100 plus minutes of lectures and 20 minutes, about 15 to 20 minutes of a break in between. So Fraser, I don't want to waste your time more. So I spent 5 minutes of your time. So I finish.
Thank you very much, Sergey, and thank you very much, especially to the organisers for the opportunity to give these lectures, either in person as was originally planned, or like this. So this is a little different to how we were originally thinking of doing this. So forgive me if things go a little bit slowly, or we have technical problems that would otherwise not have happened. So forgive me for these, but I hope that everything will go smoothly. So as Sergey said, the plan is that I will give 3 to 4 lectures now, depending on how we go, based on the notes. Hopefully you can all see the PDF that I'm sharing with you, and that Marina emailed around earlier in the week as well. And hopefully what you can also see as well is a bit of paper that I've got just to one side, just got my hand on it at the moment, which if we want to make any other notes, I will write some things there. It's a little easier than trying to write directly onto the PDF file. Hopefully you can all hear me as well. So these lectures will be an introduction to Stein's method, or the Stein-Chen method. It goes essentially by both names. Both are almost equivalent, which is a relatively recent sort of, say, mid-20th century onwards technique for probability approximations that we'll talk about. In particular, I want to focus on coupling ideas related to that. So there's a lot of material in these notes, a lot more than we will possibly get through in these 3 to 4 lectures. What I want to use these 3 to 4 lectures to do is to give an introduction to now sort of relatively classical areas of sort of Gaussian approximation and Poisson approximation in particular. So most of the time that we have will be spent on those topics. There's some exponential approximation in the middle too. The last couple of sections of these notes, let me just scroll down to see what the contents say. So the last couple of sections of these notes are essentially a little bit more recent work on more recent research results, which I probably won't get to at least very much in the 3 to 4 lectures that we have, but they're there in case we want them, and maybe at another time we can spend some time talking about those. But anyway, you have the notes, so whether we talk about them or not, there's some sort of extra material there. But as I say, what I want to focus on for the time that we've got over these next few weeks is the relatively traditional and sort of classical topics of Gaussian approximation and Poisson approximation. But before we sort of do anything mathematical, let me just sort of spend some time introducing what we're talking about. So the techniques that we're going to be talking about are all associated with proving limit theorems in probability theory. So these sort of central limit theorem, Poisson law of small numbers, they have very, very long and rich and classical history that reaches across the globe, and in terms of the areas where this was developed, various Eastern and Western mathematicians dating back to the 1700s, 1800s who've worked on these kind of problems. Let's say the most traditional of these limit theorems, these approximation results, are the central limit theorem and the Poisson law of small numbers, and they are what I want to concentrate on for these few weeks, just because they are essentially the most classical, the most important topics in some sense. And there are, of course, a whole host of techniques that work for giving us central limit theorem type results, Poisson approximation type results. We can use characteristic functions, sort of very traditionally. There are a whole host of other techniques, operator techniques that we can use. What I want to talk about is Stein's method, or say the Stein-Chen method, which is relatively recent. We're coming up on its golden anniversary, in the sense that the first paper in this area was published in 1972, so we're almost 50 years ago. But this technique has a few advantages over other methods for proving central limit theorems, for example. So although we'll start off talking about the central limit theorem, talking about Gaussian approximation, the same sorts of ideas apply in quite a wide variety of settings, as I hope we'll see. And even if we don't get to talk about the variety in these 3 hours, hopefully the notes give you an idea of other areas where we can work, and the background that we get will show how these things can apply in different areas. So one of the things I want to emphasize, particularly when we're talking about Gaussian exponential and Poisson approximation, are the similarities in the approach across these topics. So that of course we need to highlight the differences too, but I hope that the sort of unified approach to these different approximations in these different settings comes across as one feature of Stein's method. Another advantage, so often when we're talking about central limit theorems or laws of small numbers, Poisson approximation, things like that, we're often interested in convolutions of random variables. We're often interested in sums of random variables. And of course, these are much, much easier to handle if we're talking about sums of independent random variables. Independence is an assumption that makes everything much, much easier in practice. But when it comes to applications, independence is the exception rather than the rule. This is not something that we usually see in practice, except in some very nice cases, some very nice special cases. But Stein's method can handle dependence between underlying random variables relatively easily. And of course, things get harder because independence is a very nice assumption, but the idea is generalized to the dependent setting relatively easily, and that's certainly something that we want to talk about today. And so we'll usually start, when we talk about Gaussian approximation later today, we'll start by talking about sums of independent random variables, but then we'll see that if we allow ourselves to relax that assumption, things don't get an awful lot harder. A little bit more technically complicated, but not an awful lot harder. And the third useful feature of Stein's method is that what we can usually get alongside knowing, for example, that we have convergence and distribution to a Gaussian random variable, we can also get explicit, at least rates of convergence, and usually explicit error bounds in some given metrics. We'll talk more about that later on, to accompany that convergence. So we get rates of convergence which are usually pretty good. If they're not exactly the correct rate, then they're usually pretty close to it. And usually we get some explicit error bounds, so we get some constants along with that rate. Estimates of constants in these things are not usually fantastic. There's certainly room for improvement in a lot of the constants of the theorems that we're going to talk about, but that's okay. I think our interest, my interest in these lectures is more in getting rates of convergence rather than necessarily the correct constants to accompany those rates. So I said that we can apply this in quite a wide variety of settings. That includes not just the sort of univariate approximations, Gaussian and Poisson, and these sorts of things that I want to mainly talk about, but we can also extend Stein's method to multivariate settings, say multivariate normal approximation, and process level approximations, so Poisson process approximation, for example. I'm not really going to talk about those. I've indicated a couple of references in a minute, just to, if you do want to go and read a little more in these areas. But my aim really in what we're doing now is to give an introduction to the fundamental ideas behind Stein's method and useful coupling approaches to that. So hopefully, if we can get those ideas, if we can get a handle on those ideas from these lectures, then seeing how this works in a multivariate or process approximation setting is not too terrible, in the sense that we understand what method should look like, we understand what the techniques should be, and so we can go away and we can read some of the papers that deal with these more technically complicated situations, understanding the fundamentals of what we're trying to do. So, I say this is almost 50 years old now. It was Charles Stein in the late 60s and early 70s who first developed these ideas. We'll be working in a historically sort of chronological sort of way, in the sense that it was Gaussian approximations that Stein first worked on. This was as motivation for the fact that he didn't like the proof of the central limit theorem that was in a lecture course he was giving at Stanford. So he developed a new proof of a central limit theorem for weakly dependent random variables, for sums of weakly dependent random variables. And then this idea was then very soon seen to generalize to other settings. So it was a PhD student of Stein, Louis Chen, in the mid-70s, who worked on these same ideas for Poisson approximation. So these are very much the two classical settings in which this works, and that's what I want to focus on over these next couple of weeks. But since then, we've applied, Stein's method has been applied to a whole host of other approximations. Let me just skip ahead slightly. There are many references here that I've tried to give to other situations in which, other univariate situations in which Stein's method has been applied. So essentially, pick your favorite univariate random variable and either find it in that list or Google for someone having worked with Stein's method for approximations by that, and if not, then go and write a paper that does it. That's essentially the algorithm. That's one algorithm for finding topics that are worth working on is if your favorite univariate distribution hasn't had some approximation by Stein's method worked on, then go and develop it. And there's some references here for, so this is a paper that deals with, a well-written paper that deals with multivariate Gaussian approximations and some Poisson process approximations as well, in this other paper. If you want sort of entry points to literature that goes beyond what we are going to talk about over these next few weeks. So there are also some very good, there's a very good survey paper by Nathan Ross, which I think at least some of you have looked at already, which is available. Certainly parts of my notes are based on parts of this survey paper, but there's a non-trivial intersection between my notes and this survey paper, but definitely they don't entirely overlap. I should say that these notes that I'm working through are definitely biased by my own research interests, so as is probably natural. So forgive me for spending time on things that I think are interesting. They are designed to give a general introduction. That they cover everything that I think a general introduction to Stein's method in Gaussian and Poisson case should. But they are the particular topics that we cover and the amount of detail I go into in various places is definitely governed by my own research interests, and you can certainly see that from the bibliography as well. So that's, of course, that I think a caveat that goes with most people's lecture notes is that they are biased by the author's own interests, but just to make that explicit by way of apology almost.
Yeah, that's good, and that we want. Yeah, we want exactly your opinion about everything like this.
Oh, good, because I'm afraid that's what you're going to get whether you want it or not. There are also very good book-length treatments of Gaussian and Poisson approximation by Stein's method. So if you are interested in these topics and want to go well beyond the what I possibly have time and space to talk about in these lectures, so there's a book by relatively recent book. I think this is 2011, I think, so not too long ago, by Louis Chen, Larry Goldstein, and Qiman Shao, who talk about normal approximation. And there's a slightly older book, so this is from the early 90s, 1992, I think, by Andrew Barber, Lars Holst, and Svante Jansen, who talk about Poisson approximation. And they also, if you like the sort of coupling ideas that we talk about, and in particular the size bias coupling that we talk about when we get on to Poisson approximation, then that's essentially the approach that's taken throughout that book. So there are an awful lot of examples in that book, if you want to go and see Poisson approximation examples in practice, and also a more detailed discussion of the theory, at least as it stood in the early 90s. There's obviously been a lot of work since then, but that book is very well written and is still an excellent entry point to Poisson approximation. And let's say the book on normal approximation is much more recent, so it gives you a lot more of the sort of a modern take on Gaussian approximation using Stein's method. So as I said already, with Gaussian approximation, there's a little sort of interlude on a relatively short interlude on exponential approximation, so approximation by an exponential distribution, because I want to emphasize are the similarities of this technique applied to various different limiting distributions, and it's sort of easiest to do that by looking first at two continuous random variables, because then it's very, very clear what the similarities are. So after treating Gaussian, I want to sort of step away from the historically correct order in which to do things and look instead at exponential approximation, which was done a little bit more recently, before we then look at Poisson approximation after that. Let's say there's a last couple of sections which I almost certainly won't have time to talk about in any detail in these 3 to 4 weeks, but which I might just give you a brief guided tour of at the end of my last lecture to show you what there is, and maybe at some future point we can either talk about those in more detail, or you can take the notes and work through those if you're interested. Okay, so that was just, okay, so this is all things that we've already said. Let me just scroll ahead a little. So the starting point of this whole idea is a relatively simple one. The observation that leads onto this whole theory that I can happily spend 3 or 4 lectures and more talking about is a very, very simple observation that if I take a standard normal random variable, okay, I want a standard normal random variable to mean 0, variance 1. The assumption that the mean is 0 and the variance is 1 isn't doing anything interesting. It's just to stop us having sigma squareds kicking around for the variances and things like that. We can always standardize the problem so that the things we're interested in approximating have mean 0 and variance 1. So that's not doing anything very interesting. But if I have a mean 0, variance 1 Gaussian distribution, let's call it Z, then for reasonable functions f, okay, reasonable functions so that everything I'm about to write down is well defined. Right? Let's not get beyond that at the moment. That the expected value of f primed of this standard Gaussian random variable is the same as the expected value of z times f of z for any reasonable function f. So it doesn't seem very deep on the face of it, but it turns out that there's an awful lot you can do with this and with things like it that work in other situations as well. You can think about this as an integration by parts, essentially. The fact that holds, that if I have a Gaussian random variable z, the fact that that identity holds is essentially integration parts. If we ignore exactly what functions f we want, and if I am very lazy and don't worry too much about technical details and exactly what properties this function f should have, well, then so if I write over here, hopefully you can all see it. Please tell me if I need to write a little bit larger or a little bit clearer in other ways. But let me just write down. I'll start with some inverted commas to mean that that what I'm writing down is extremely loose. But is that okay? If you can see the expectation symbol, hopefully.
Yeah,
is that large enough? That's large enough for everyone to see. Good. So what's the expected value of f primed of my standard normal random variable? So that's just an integral of my, say, f primed of x times is a 1 over root 2 pi that's not doing anything very exciting. We'll just carry around as baggage, e to the minus x squared upon 2 dx. And well, I say, let's not worry about exactly what functions f I'm allowed to do this for, right? I'm absolutely not going to worry about that for now. But more or less, if I integrate by parts, so I integrate the f, I differentiate the density function, that brings down a minus x from that exponential, and so I'm going to end up with a term which I integrate by parts. I'm going to end up with 2 terms. One of them goes away because let's write it down. I suppose I'm deliberately being informal. So what do I get? I get a
minus.
Sorry, forget that. Turns out helps if one can integrate with it. So I get this term, which is going to disappear because essentially the exponential goes away, right? If you have reasonable functions, then that e to the minus x squared is going to go away as x goes rather infinity or minus infinity. So that term isn't going to end up doing anything, and what's left is just exactly what I want, in that there's a minus sign that's gone there already, but I'm going to end up with with exactly what I want, which is just the expected value of.
You forgot a baggage with square root of 2p.
I forgot my baggage. Thank you very much. Yeah, I need to carry around with me. It does absolutely nothing. But,
yes.
Yeah, thank you very much. So I say I'll put that in inverted commas because I'm not at all worried about what functions f that works for. But okay, that's just integration by parts, right? I mean, to see that is not too complicated. You do have to work a little bit harder to see exactly what functions f you can write this down for, and we will do that work later on. So I promise a more precise statement of this result a little bit later, but let's just get the idea of what we're doing. So I know this integration by parts argument has convinced us that if I'm standard normal, then this holds for all f. The observation beyond that is that the converse holds true, holds as well. So if I know, maybe I said this later on. So no, I don't quite yet. So if I know that this holds for some random variable z and for a suitably large class of functions f, then that tells me that z has to be standard normal as well. Okay, so I'll make a precise statement of that later on. But this works. This isn't just an identity which is satisfied by my Gaussian. It serves to characterize my Gaussian in that this holds for all f within a suitable class, if and only if my z is a Gaussian random variable. So it really pins down the fact that what I'm working with is Gaussian here in some sense. So okay, if I know that this is true exactly if I happen to be Gaussian, so this is true for all f if I happen to be Gaussian, well, if I can find some random variable, let's call it w, this is often a traditional way of denoting these things, that I think is approximately Gaussian in some sense, right? Again, this is a high-level, imprecise discussion. So, but if I think that this random variable w is approximately Gaussian, then maybe this holds at least approximately in some sense, whatever I mean by this. So maybe we think that for a suitably large class of f, what we have is something like this approximate equality, where I absolutely am not telling you what I mean by approximately equals, but let's just. And so somehow, looking at how big the difference of the expected value of f prime and w versus the expected value of w, f of w is, so how big the difference between what's on the left and what's on the right is, gives me some kind of measure of how far I am away from being Gaussian. Intuitively, that sounds reasonable. It also is intuitively, well, I think I haven't yet told you that this is going to make the problem any easier than the thing we started with. So somehow we want to check in some sense or prove some limit theorem that says that w is asymptotically Gaussian. There's usually some n kicking around somewhere, some parameter n that inside w that we want to let go to 0, like the number of terms in a sum or something. So if I know that this is approximately Gaussian, I want to sort of quantify that in some sense. I want to show the limit theorem. It's not yet clear that this is going to make life any easier, but certainly I should be able to, at least we think, that the difference between what's on the left and what's on the right here should in some sense, at least how big that difference can get over a suitably large class of functions f, should give me some sense of how far w is away from Gaussian. And one of the real insights that Stein had when he was doing this, so he saw a way to make this reasoning precise and to work for a variety of different ways of quantifying distance between my random variable w on one hand and my Gaussian random variable on the other. And the key to this is to write down what's sometimes called a Stein equation. So this is my Stein equation for a standard normal random variable. And so it takes a little bit of thought to see why I've written down what I've written down, but when we're sort of familiar with how this works in general, we can see what we want to be writing down in these Stein equations. We can understand fairly quickly what we want to write down. So to start with what's on the right-hand side, so what's on the right-hand side is essentially a rewriting of terms that come from this characterization or this that I had of my Gaussian. So my characterization was telling me that the expected value of f primed of the Gaussian, call it z, was the same as the expected value of z f of z. So I'm essentially writing down terms that come from that in such a way that if I replace my deterministic little x's, so little x is just some real number here. So if I replace I replace my x's here on the right-hand side by, say, my random variable w, and then take expectations, I get exactly the difference between expected value of f prime of w and expected value of wf of w. So I get exactly the difference that I want to use to be able to quantify how far I am away from Gaussian. So what's on the right-hand side has just come straight from this characterization that we started with. So then what have I written on the left-hand side? so if what I'm going to do is replace these little x's by my random variable w, and then take expectations, then that's going to give me on the left-hand side the expected value of h of my w minus the expected value of h of z, where z again is Gaussian. And that's something I can use to relate. That's something I can relate back to ways of quantifying, ways that I understand of quantifying how far w is away from Gaussian. I'll talk about that in just a second. Well, the other thing we should say about this, so I'm thinking of, when I write down this equation, I'm thinking of h as a function that I know, so some test function that I understand, that I know how it behaves, and I'm thinking of f as a solution to this equation. Okay, so think of f as depending on the h that I give you. So in this equation, h is something that we know. It's going to be some nice, well-behaved function that we understand. F will be the solution to that equation, which will depend on the function h. So f is, well, we haven't said anything about what f looks like. It's potentially rather complicated or whatever, but anyway, there is some. We'll convince ourselves later on that there is some well-behaved function f which solves this equation. But then once I've done this, so I'm going to use this Stein equation by replacing my x's by my random variable w, taking expectations, and then what I want to do is use what's on the left-hand side to understand exactly how I'm measuring how close w is to Gaussian. Because I can think about metrics, whole families of metrics, which look at essentially how big that difference is, the difference that I'm going to get from the left-hand side of my Stein equation, how big that difference is, or at least the absolute value of that difference, slightly more precisely, as I let h vary over some wide, rich class of functions. So if I take my Stein equation, I replace my little x's by w's, I take expectations, then I take absolute values, and I take the supremum over h's living in some nice family, some nice big family, then I can get some well-known ways of measuring how far w is away from Gaussian.
And why you need f of 0 equals 0?
I don't. So my Stein equation doesn't tell me what f of 0 should be. So let's pin it down as being 0, just to give it a number. But it's a good point, and you're actually free to choose what you want that to be. So in a minute, we're going to have to talk about how this function f behaves and to give some bounds on how it behaves and things. If choosing a different value of f of 0 gives you a bound that you want, gives you a nicer bound on the way f behaves somehow, then feel free to choose that. And that's certainly done in some proofs in some cases. So that's not essential, but it just.
Okay, thanks.
It's there to make the solution unique at this point, but I don't really care what value I choose. That was a good question. Are there any other questions? This is maybe a reasonable time to pause for.
Yeah, I will remind that you can ask questions on the chat if you want, or you can use microphone as well.
That's also true. So, thanks. Okay, so let me just say a little bit more about these kinds of metrics that we can talk about when I want to think about assessing how close w is to Gaussian. So there are lots of metrics lots of well-known metrics that I can talk about in these settings. So the Wasserstein distance, for example, looks exactly like this, and that formula is the same as the one above, only I've specified exactly what class of functions I want to look at, which is just here the class of Lipschitz functions with Lipschitz constant 1. So if I take this particular family of functions h that I want to take the supremum over, this gives me precisely the well-known Wasserstein distance, or at least a linear Wasserstein distance of order 1. There's a whole family of Wasserstein metrics that you might want to think about, but this gives me the linear Wasserstein distance of order 1. As Sergey pointed out shortly before we started, we get some slightly odd notation here. So the Wasserstein distance I'm writing as d sub w, so as Wasserstein distance. There's a different w to the w here, which is the random variable that I want to be approximately Gaussian, which I think is somehow approximately Gaussian. This is essentially bad notation that has somehow been adopted in the literature. Many papers use w for the random variable that I want to approximate here, and I've stuck with that because somehow I've written too many papers where that's true for me to ever write anything different without some huge amount of effort and lots of typos probably along the way. So apologies for the slightly odd notation perhaps, but this w, the subscript w here stands for Wasserstein. The w here inside the bracket stands for the random variable that I want to approximate. So this is one of the possible family of Wasserstein metrics, and it's the one that we're going to work with. I guess as a side comment, in these sort of whole family of Wasserstein metrics, there are I can write Wasserstein metrics of order 1 like this, in this sort of way, where I have to specify what class I'm taking, what class of functions I'm taking the supremum over. Wasserstein metrics of higher order, if you're familiar with those, don't have a representation like this. There's no sort of dual representation like this. So I can't deal with those in the framework that we're talking about. What I really need is a metric that can be written in this way, where I take the supremum over some class of functions of the difference in the expectations of this function h applied to w and applied to z. So to write down what I want, I really do need a metric that can be written like that, which is one limit on the family of metrics that I can possibly think about. Anyway, I can cover lots of interesting metrics, so that's okay, but just as a side comment. Just one other for now metric that I can think about in this setting is the Kolmogorov or uniform distance, which just looks at the largest difference between the distribution functions of w and z. So in that case, I can just take this class of functions h just to have a lot of indicators of half lines, so that when I take expectations, expectations just become the probability that my random variable is less than or equal to some given number. And let's see how big I can get as I let that given number y vary. So I can when it comes to Gaussian approximation, we'll limit ourselves to thinking about Wasserstein and this Kolmogorov distance, but we can think about other things, and we'll look at total variation distance later on when we talk about Poisson approximation, and that falls in this framework as well. Okay, so those are the sort of metrics I can think about. So what my Stein equation is telling me is that I can think about assessing how close w and z are in whatever metric I'm working in that has the right form by looking at how big this right-hand side can be. I look at the difference between the expected value of f prime of w and wf of w, those terms that I got from that characterization of my Gaussian distribution. And at this point, it's really not clear that what I've done is make the problem any easier. So somehow I've taken a metric that perhaps I understand quite well. Wasserstein and Kolmogorov distances are things people have been studying for many, many, many years and understand quite a lot about. And I've said that I'm going to bound that by looking at this object here on the right-hand side, which now contains some function f that I really don't know anything about at the moment, and also depends in a sort of significantly more complicated way on this random variable w, perhaps than what I started with on the left-hand side. And so you'll be forgiven for thinking that it's a sort of nice way of rewriting the problem, but doesn't really get you anywhere. But it turns out that it does get you somewhere. And I think perhaps intuitively, one of the reasons that this buys you something is that now on the right-hand side, I don't have any z's kicking around. So I've only got a single random variable w that's living on the right-hand side there. And so somehow I've turned this bivariate problem, where I would really have to think about coupling w and z, constructing them on the same probability space and seeing how close they are when I make some particular construction. I've turned that sort of bivariate coupling problem into a univariate problem, and that somehow buys me enough to make this whole approach work, which I think is not at all obvious and when the first time you see it. So now, now, having sort of essentially rewritten the problem like this, what I need to do is think about how I can actually work with what's on the right-hand side there. And there are a whole host of techniques that will let you try and get a handle on what's written there on the right-hand side. We're going to talk about at least 4 or 5 of them in varying amounts of detail over the next, well, today and possibly a little bit next week. I don't know exactly how quickly we'll go, but there are a whole host of different techniques for trying to bound what's on the right-hand side there. So somehow, the key insight from Stein's original work was that this representation is a useful way of getting a handle on these distances between w and z, but there are very much there's a large number of ideas which have been worked on since then and which have been developed since then for actually doing that in practice and working with what's on the right-hand side there. So I want to talk a little bit about some of those. But before we can do that, there's just a little bit more that we need to say, just to, well, firstly, to make this all just a little bit more rigorous. Let me give you a statement of a lemma or two, just to make sure that we're sort of on solid ground in some sense. And also the other thing I'm going to need to know before I can think about bounding this right-hand side is how this function f behaves. So let me just go back up a minute to the Stein equation that we defined up here. So I said that f was a solution to the Stein equation. We know what the function h is. H is maybe some Lipschitz function or some indicator function, something like that. Now I need to know about how this function f behaves. One key point when it comes to thinking about understanding how f behaves, so we're going to want to bound things like how big f can be, how big the derivatives of f can be, things like that. That doesn't at all depend on any random variable w that I might want to be approximating by a Gaussian. So there's essentially nothing random about that equation. Right? There's a Gaussian random variable z that I've written down, but that's only there as part of this constant expectation. So there's nothing random in this equation. That's just a differential equation. There's nothing. It's not even a particularly complicated differential equation. And so when it comes to writing down an explicit expression for f, and when it comes to bounding how f works and how f behaves in practice, that firstly can be thought of purely as a functional analysis problem. Okay, there's not necessarily any probability there at all. You can find nice probabilistic arguments that tell you things, but you can, if you want to, think of that as just bounding the solution to this given differential equation. So there doesn't have to be any probability there, and that doesn't depend. Secondly, that doesn't depend on the particular random variable w I'm interested in. So once I've got bounds on how f behaves, that will work for any Gaussian approximation problem that I want to tackle. It doesn't depend on what particular random variable w I want to be working with, which is nice. So finding bounds on that f is essentially one-off work that you do at the start of thinking about Gaussian approximation. You don't have to redo this work in any way when you want to think about approximating some different random variable w. So okay, let me head back down again. So okay, here's a more precise statement of this characterization that I promised you earlier. So this formula in the middle of this lemma is one we recognize. This is the property of my Gaussian random variables that we've used to build up the theory so far. And this is a slightly more precise statement of the lemma that makes it clear that this is a characterization, that this is an if and only if result. That if this holds for all suitable functions f in this nice family, it's actually absolutely continuous, so that expectations are defined, then if this holds, then this random variable x has to be Gaussian, and if x is Gaussian, and then this holds for all nicely behaved f. I'll show you a proof of that lemma in just a minute, but not quite yet, because I'm going to there's a little bit of work I want to do before I prove that, but anyway. So the as I say, the Stein equation that we're writing down in the Gaussian case is an ODE. It's just an ordinary differential equation. It's not particularly complicated, ODE even. And if you want to write down an explicit solution for that, then there it is. So what's inside the integral here is not that exciting. This is more or less this is what I had on the left-hand side of that Stein equation. So just essentially a renormalized version of my function h, where I've just taken off the expectation of h of a Gaussian, and then all I've got is essentially the density function of my standard normal inside there, and 1 over that outside there. All this baggage we had to carry around before cancels, because there's a sort of essentially 1 over root 2 pi that comes from both of those. It's not a difficult ODE to solve, so I'm not actually going to do that for you. But if you want to just check that what I've written is correct and typo free, there may of course be typos in these notes. I tried to read thoroughly, but if you find typos, then please do let me know, because I'd like to correct them. But anyway, one of the easiest ways to get a handle on that solution is just on solving that ODE is just to use an integrating factor. It's essentially the density of a Gaussian, if you want to. And then, but once I've got an explicit expression for that, it's then not too terrible to go away and find bounds on how that behaves. There are lots and lots of different bounds on this function f that you can find in books and papers, because essentially different bounds on f are useful for different applications, depending on exactly how you tackle your Stein equation, depending on exactly how you bound what was on the right hand side. I wanted to show you just 1 or 2 bounds on this function f. So there are a whole lot more. I'm just going to pick the couple that we will actually use for the things that we'll talk about later on. All of these bounds are just written in terms of a supremum norm. So just the infinity norm just telling me how big a given function can be. So probably the most useful bound on how this solution f to my Stein equation behaves, it tells me that if my function h is absolutely continuous, so if I've got some essentially differentiable function h that I start with, then I can bound the second derivative of the solution f to my Stein equation in terms of the first derivative of my h, which is the constant 2 that appears out the front. So that's probably the most useful bound that there is, in the sense that it's the one that's most commonly applied in these kind of problems. But there are a whole host of other bounds. We can find bounds on f, on its first derivative, on higher derivatives as well, which might need some more or less relaxed conditions on h. So we can find non-uniform bounds that tell me how big f of u can be in terms of u and things like this. And here's another non-uniform bound, which I'm not going to say very much more about, but it turns out to be useful in one particular setting, essentially just to give you an indication of the kinds of slightly more exotic things to do with f that we can bound. It essentially tells me a difference between, it's more or less x f of x, which you can sort of imagine how that might appear given that terms like that appear on one side of my Stein equation. The difference between that, between x f of x and y f of y in terms of how far apart x and y are.
We have a question.
Yeah.
Maybe it's a good time to answer.
Yeah. Go for it.
Nikolai asks, which paper contains exact bounds with optimal constants? Book of Chen and Shao, 2011.
Yeah. So this constant 2 is optimal. You can show that that's Shao. And yes, the book by, where's this? So that, I think 19 is the book by Chen and Shao. Sorry, Chen, Goldstein and Shao. It certainly should be. And yes, they have lots of statements of these kinds of bounds. So it's not exhaustive in that there are other bounds that have been used and which appear in the literature, which aren't given in a couple of lemmas in that book, I guess, because they just don't need them. But that's a good reference as a starting point. That's
okay.
That gives you a much wider selection than I've essentially than I could be bothered to type out, because we didn't need any others. So I left it with just these two. But yeah, there are lots of other bounds there, and proofs of all of these as well, of course. Were there any other questions at this point? Because that probably is a good.
Maybe it's a good good time for a break, for a small break. What do you think?
Yeah. So let's see what's. Yeah. Let me just show you. I wasn't planning to say very much about the proof of that, but let me just show you the proof of that, and then we'll take a break. That sounds good. So I'm sorry, I'm scrolling around a bit madly. So I'm not going to say anything at all about the proof of this second bound, but the proof of the first bound is written in the notes. I don't want to say very much about it. I wrote it there because I like it, because it was essentially generalizing this first bound was the thing that got me the first paper I ever had published, sort of 10 or 12 years ago, whatever it was. So I sort of I have some fondness for this, so I wanted to show its proof, because essentially it's a result which has a special place in my heart. but the proof is there partly just to emphasize that you can, if you want to, think of this just as functional analysis. So there's nothing particularly complicated happening in that. So I can differentiate my Stein equation to get an explicit representation for the second derivative of f in terms of f and h and its first derivative. I then essentially do a little bit of work just to find a way of writing that, writing this term. I'm writing it in terms of the distribution function of my standard normal. A little bit more analysis will get me essentially, it's sort of one way of approaching it is to look at the ratio of the distribution function of my standard normal to the density function, use some properties of that, and that just allows me to get a handle on all the terms which appear there. So I'm going to end up using the triangle inequality. There's an h prime there. H prime is what I want to bound this in terms of. So I just need to write it in such a way that all that lot, the absolute value of everything else appearing there, isn't bigger than the largest that h prime can be, and the supremum normal of h prime. And so just some work to be able to write what I want. So there's that should be an h primed, I think. Hey, I spotted a typo. That should be an h primed, but essentially some work to get a representation on everything else that's in there, and then shows that everything else, the absolute value of that's at most the absolute value of h prime. Just bring a supremum of h prime out of these integrals. So that should be an h primed. That first term there in equation, is that 11? I can't remember. Yeah, so that first term on the right hand side of equation 11 should be an h primed. But okay, I don't want to go into details, but that's probably a sensible place to stop. Should we say 10-15 minutes? What do people want as a break? What's reasonable?
Yeah, I think 10-15 minutes, but let's make it more explicit. So
should we say 10 past the next hour? So I think it's almost 5 o'clock where you are, I think.
Okay. Yeah. Yes.
So should we say 10 past 5?
Okay. Good. 12 minutes for the break.
That sounds good. I'm just going to go and get some more water, but I'll be back in a second if people want to chat a little over the break. Then I'm happy to discuss a bit. But I'll
okay. Yeah. Good.
Refill my water first.
Okay, the lemma 2.2. I have a question about it. If I can ask.
Yeah, go for it.
I mean, it is the same question. F of 0 equals 0. It's look like H should be like in some sense symmetric or no? To have F of 0 equals 0 or wrong?
So.
And maybe there is like problem with constant like square root of 2p.
Yeah.
I'm not sure. Or maybe no.
So if it's a good question. I don't immediately see the answer, but
okay. So yeah,
it's look like if h of y will be a symmetric one. It's not symmetric.
It doesn't have to be symmetric.
But yeah, but it shouldn't have to be. So.
Okay.
So
lemma 2.2 just say that it is the solution to Stein's equation 1, but it doesn't. But again, like if you look at equation 1 before that, it says f of 0 equals 0, but it's not necessarily reflected in lemma 2.2.
It should.
Okay.
Yeah.
I mean, I just wanted to see like this. Maybe it's wrong one, but like all solution of this differential equation. Yeah. I mean, with this like undefined constant.
Right. Yes. Yeah. So setting f of 0 just gets rid of that constant.
I mean, no problem. Yeah, understand that. Yeah.
Yeah.
You said how to derive the solution, and it was I think it's after some time we can do it.
Yeah.
Maybe tomorrow on a student seminar again. We have we should say this. Yeah, tomorrow we have this student seminar. It's called student seminar, and it is seminar for students. And we will understand the first lecture of Fraser on it. Everyone can come
Welcome
to us. Welcome. Yeah, thanks.
So the pacing is about right, Marina, you think? Or you want me to? You think I should go a little faster, or everything is?
No, I think it's fine.
It's fine.
At least I understand everything you say.
I'm being, I think, relatively slow, but that's deliberate because I think at this point we want to understand everything, right? It's not like we have. I'd rather.
For me, it was a good speed as well.
Yeah, good. That's good.
But we have also another participants. So like if the speed of the lecture was fine for you, send please plus to chat. They always ask you.
Oh, yeah, like so.
Yeah, and if it was not good, then you need to send something else.
I think it's fine for the most of the participants.
Seems fine.
Yeah, and I think we can continue the lecture.
Yeah. Okay. Yeah. Let's carry on. So I'll try and keep this chat open, but I'm trying to look at my notes and everything. So if I miss questions in the chat, then please do exactly what you did in the first hour and interrupt me. This is
Okay.
this is exactly the correct thing to do. So I think everyone is ready for me to start. I think is that. I think we are.
Yes. Yes.
So I feel like I do owe you a proof of this lemma 2.1 as well, which gives us the characterization. Just to have it recorded on paper, just to make sure that we're happy. So this is I put this slightly later because we're half of it's going to rely on having this function f that solves the Stein equation. So if I want to, so the characterization that we had was an if and only if result. So half of it said that if this random variable x is Gaussian, then expectation of f prime of x is equal to, what do we end up with? Expectation of x f of x. And essentially the argument is integration by parts, this argument that I sort of very roughly sketched over here, only this is the integration by parts argument done properly, in the sense that it's being a little bit more complicated because it's letting us get a handle on the widest possible class of functions. Integration by parts is this argument works on some slightly more restricted class of functions, but let's just make it's essentially integration by parts, just with just made a little bit more complicated to let us get a wider class of functions f. So for the other part, which I've said almost nothing about the proof of so far, essentially we can use the fact that we know what the Stein equation, or what the solution of the Stein equation looks like, or at least that we know that a bounded function of that Stein equation exists. So that will let me write down. So if I take this Stein equation, maybe it's worth writing the Stein equation down, just so we all, this is the best way to have everything in front of us. So the Stein equation that says that h of x minus expectation h of my Gaussian z is f primed of x minus xf of x. So that's my Stein equation. We'd called that, I think it was called 1, but I'm not going to write that down because I'm not entirely confident of that number. But what we've just said is we know that this solution to that that we've defined that we've written down explicitly, and that just before the break we found some properties of. I know that that's a nice continuous, differentiable, and bounded function. All these, okay, I guess all we proved explicitly in lemma 2.3 was that the second derivative was bounded, and that some. But anyway, it is a bounded function. It's not too hard to find a bound on that function f. And so, if I know that then I know that function f that it's in my Stein equation is a well-behaved function that falls within the family that I'm thinking about within this lemma, the family for which this characterization works. And so I know that well, by assumption of my lemma, this expression here is 0, but that's what was on the right hand side of my Stein equation. Replace my x's by w's and take expectations on the left hand side of my Stein equation. And what I get is exactly this: the difference between the mass function, the distribution function of this random variable x, and the distribution function of my standard normal z. So because those two things because that difference is equal to 0 by the assumption that I'm making, then that tells me that x and z have to have the same distribution. So x has got to be standard normal. So proving one half is integration by parts to check that if I'm Gaussian, then the identity that I want holds. Proving in the other direction just relies on the fact that I'm writing down this Stein equation, that I know that the solution f is well behaved, and so that so I can, by assumption that I can get the expectation of this thing is 0, then just write down what my Stein equation tells me that is. So it's not too terrible, but I think we are, in general, in these kinds of characterizations, proving the sufficiency is a little bit trickier because I do need to know a little bit about this function f that solves my Stein equation. Okay, so what I want to spend the rest of today and probably a bit of the start of next week thinking about as well is how we actually use this idea to get some explicit bounds. So I know what we've done so far is, sorry, I'm scrolling quickly, but I'll stop in a second. What we've done so far is motivate the fact that I can get an explicit representation for some distance, say my Wasserstein distance between W and Z, that I have this particular representation. Okay, that I can write this in terms of some expression, an expression in terms of f and in terms of my random variable W. And what I want to do now is understand how the heck I actually work with what's on the right hand side there, how the heck I actually bound this thing, so that I can bound, say, my Wasserstein distance between W and Z. So as I said already, there are a whole host of techniques to try and do that. I think I'd maybe talk about, in various amounts of detail, 5 different ways that you can think about doing this in these notes. So some of them I'm going to go over with essentially no detail. Some of them are going to a bit more detail. That's partly down to time and space constraints, partly down to my own preferences. But that's what I want to do is show you at least a little bit of everything, so that at least if you want to learn more, you know the right terms to go and search for. You know, you've got some references to try and work with. Is my aim. So I'm absolutely not going to give you all details of every approach. But hopefully enough that you are familiar with the key ideas, and you know what to go away and start looking for, and also enough detail for at least some of the approaches that you can see how these proofs generally work, which will hopefully help you if you want to go and read other proofs. You at least are familiar with the kind of techniques that are needed. So anyway, the first example to think about, because it's by far the easiest, is what happens if I happen to have a sum of independent random variables. So as I say, Stein's method definitely works in if I drop the independence assumption, but things are of course much easier if I do happen to be independent. And so it's a reasonable example to start with. So I'll show you sort of one way of tackling this case of the sum of independent random variables. It's an example we'll revisit a few times looking at it in a few different ways, just to see how different techniques work in this kind of setting. But I want to start off by thinking about perhaps the most direct way of getting a handle on Gaussian approximation for a sum of independent random variables. So I'll have a sum of n of these things, call them x1 to xn. So my W is just the sum of n independent random variables. We're going to think about n going to infinity in some sense, but as is typical with these bounds, what I don't get is just a rate of convergence. I get an explicit error bound for any given n. So what we hope is that the error bound goes to 0 as n gets large, but I certainly don't need to think of this only as an asymptotic result. I can think of this as an explicit error bound that I can apply for any given n, whether it's 10, 50, or 100 or whatever. We'll normalize everything, because that's the easiest way of dealing with getting us mean zero and variance 1. So I'll just assume all these x's are normalized to have mean 0 and normalized so that their variance is sum to 1. So,
and what about the constant 4? Is it optimal or not? Is it known as like optimal or not?
So it's definitely not optimal.
Okay.
So with with these kind of bounds we get to Stein's method, usually the order is correct. So the fact that we get a sort of sum of third moments is the right sort of thing. So that's what you'd expect. It gives us the right order. The constant is definitely not optimal. Stein's method does genuinely quite badly with constants.
Okay.
It usually gets the right sort of order, though there are definitely examples where it goes very badly wrong in the order as well. I don't think I would include the example I'm thinking of in the notes, but anyway, I can show you an example if you want later on in a approximation setting where it actually gets the order very badly wrong, but usually gets the order about right, but the constant it usually is terrible for. So there is an explicit constant. It's definitely not the best one.
Okay.
It's usually true for these kind of results. So, okay, we'll go through the guts of this proof in quite a reasonable amount of detail, because it at least gives us an idea of what it is we want to do. So useful to think about this notation. So I'll write wi to be the sum of all of my x's apart from the ith. So take the sum of all of them and subtract xi, so the sum of all of my other n-1 x's. And what I want to bound is this thing. So that's what I had on the right-hand side of my Stein equation. That's exactly the representation I had for my Wasserstein distance. And more or less, any sort of idea that at least most of the ideas that I want to talk about so this week and next week are all sort of the flavor. Let's try and write expectation of f of w as expectation of f primed of something plus maybe some kind of remainder term. So I essentially want to try and take this f of w and express it in some sense in terms of first derivatives at f, because that will at least let me do some kind of, I can unbound this fairly sensibly. So let's think about playing with this expectation f of w. So it's not too terrible. The first thing I can do is write this w as just a sum of my x's. So that's my w essentially. And for every I, that w is just wi plus xi. Oops. So all I'm doing is writing wi plus xi there, and writing this as a sum of my x's. Then, perhaps not surprisingly, a Taylor expansion is a sensible sort of thing to do. I mean, that's a reasonable way of taking yourself from f's to f primes, is to use a Taylor expansion. So just expand. So look at what's inside the sum here. That's what I've got here. Then just expand that around my wi. So I've got a term involving f's, and then I've got a remainder term that involves f primes. That term that involves f's is going to disappear when I take expectations, because of my independence assumption, because my xi and my wi are independent. So this is certainly one place where I'm going to use my independence assumption. Definitely there will have to be some kind of changes when I want to drop that independence assumption, but for now, independence tells me that xi and wi are independent, and so when I take expectations, that first term is going to disappear. So all I'll end up with is this remainder term involving some f primes, which will end up looking like that when I put the expectation and the sum back. So now let's just play a little bit with the other part of what I have on the right-hand side, my f prime term. So to do essentially nothing for a few lines, I'll just pop in the sum of put in the variance of my w, just a sum of the variances of my individual x's, which I was assuming out was 1. I've normalized it so the sum of those variances was 1. And then I'll just add and subtract what I get if I replace that w by a wi. So essentially doing a whole bunch of nothing, which is multiplying by 1 and adding a 0. But you know, we'll do it slowly because it's worth. I want to convince you there are no tricks hidden up my sleeves. The second half we'll leave alone. Again, we can use. Well, I can write this variance as the expected value of xi squared because my x's have mean 0, and then again just use independence. So there's again, we definitely are making use of an independence assumption, but I think not in such a fundamental way as if we were trying to tackle this problem using, say, characteristic functions, where somehow on the first line you end up using independence, and so somehow it's a little so it's a little easier to see that we might be able to get away with dropping independence than if we were doing something like characteristic functions here. So okay, I've got a representation for the expectation of f prime of w. I've got a representation for the expectation of wf of w. So now let's just pop all those together. And then all we're going to do is, so I've got this thing just as a reminder. Let's just scoot back up. What I wanted to do, the bound for my Wasserstein distance, it will be exactly a bound for the absolute value of that thing, and then with the supremum of h over these Lipschitz functions. So all I want to do is take this representation. I'll bound these two terms separately, just use the triangle inequality. So I want to bound for each of these two terms in this representation. I'm going to bound the, I'll take absolute values and see how big that can get as h. Remember, this function f depends on that function h, as h varies over all my Lipschitz functions. And that's just so I use the triangle inequality. I'll end up taking my absolute values inside the integral. I can bound this difference of f primes in terms of the second derivative of f, and I'll get an absolute value of x out of that as well, which will go with that xi squared to give me a to give me an xi cubed. Do the same thing for this second term. I'll get a sigma I squared, but that's all right. I can combine. I can take my sigma I squared together with the xi that I'll get out of where's my, oh yeah, the xi that comes from the second derivative bound, sorry, yeah. And I can bound that in terms of third moments as well. So do exactly that, bound what's inside these integrals using mean value theorem, bound them in terms of second derivatives of f, because the difference between what's inside these two, what's inside my f primes here is just u times xi. And then, so then to get the bound of my Wasserstein distance, all I need to do is take the supremum of this over all of my overall Lipschitz functions, h Lipschitz with constant 1. But but I know how that works, and I already have a bound which tells me that dilemma that we looked at just before the break tells me that this supremum norm of my second derivative of f is at most twice the supremum norm of h. H is Lipschitz with h prime. Sorry, h is Lipschitz with Lipschitz constant 1. So this supremum norm here is at most 2, which gives me the constant 4 that we had in the theorem. And then this from a Lipschitz function is that for the Lipschitz function I'm thinking about, that term is just 1, so that gives me exactly what I want. Does that proof make sense? Were there any questions on that?
For me, it's okay. Maybe some comments. I mean,
yeah,
they're
if there are
just
questions
simple
or comments.
ones. That, like, if we have that the sum of second moments equals 1, that means that each random variable in some sense is small. It's like 1
Yeah.
the square root of n. Yeah? And this means that the third moment, the sum of third moment, will be small as well.
Yes, yeah, exactly. So that's why this is a reasonable error bound. Yeah, this is going to go to. So this will, because of the way we've normalized this will essentially look like 1 over the square root of n. Sort of. Is that right? Yeah.
Okay.
So yeah, so this is going to become small as n gets large. And any other questions or comments? If not, I have a couple of comments on the proof, but I'd rather you all contributed first before I sort of go too deep into other things.
Do not hesitate to ask the question to Fraser, let's say comments. I mean, we have a lot of students and mostly they always speak a lot, but nowadays we speak in English and maybe it's a small problem for us. We need to just get used to it. Anyone wants to ask a question? Usually there are like 4 voices that like everything is clear, go further and so on, but now everyone is
yeah, I think, yeah.
because of the English, yeah, not because of your lectures, or
yeah.
okay,
So I don't know. Organizers will be happy if questions come in Russian, then perhaps the organizers could interpret for me. That's also an acceptable way to ask questions. I think if I can volunteer your services in that way.
Yeah, we can do it. We can do it that way. I will use like my I don't know, status, and we'll ask directly someone. Pasha, everything is clear.
Yeah, everything is clear.
Okay. Thanks.
Let's so I guess one thing about this proof is, so there's kind of at least some parallels between this and the sort of leave one out type arguments from the sort of Lindeberg central limit theorem type proofs. There's at least some parallels you can draw. There's some similarities in that somehow we're throughout this proof kind of distinguishing some particular, well, all of them separately, but at each kind of point we're sort of looking at taking out each I. So there's at least some sort of parallels between those and the sort of Lindeberg type leave one out arguments. And I guess the other thing to say, so at some point we used, so the bound that we had on this second derivative of this solution f to my Stein equation was very useful. Being able to use a bound on that relied on the fact that my h was differentiable, but the underlying h that I was thinking about here were differentiable functions. And that's great if I'm doing what I'm doing now and thinking about Wasserstein distance. It's not so great if what I wanted to do is think about Kolmogorov distance. So essentially the biggest difference between distribution functions, because there my underlying h's were indicators, these indicators of half lines, and that's definitely not going to be a good thing in the sense that those are definitely not differentiable. I can't apply a bound on the second derivative of f. The sort of more generally, the smoother the function h is, the easier it is to work with. So that's because the smooth. It's because sort of essentially f, the solution to my Stein equation, gets its smoothness properties from the h that I started with. So we saw already that if h is differentiable, then my f is twice differentiable. And in general, if my h was twice differentiable, my f would be 3 times differentiable, and so on. So if h is not differentiable, then I can perhaps get one derivative out of that, but definitely nothing more. And so I'm going to have to work a bit harder to get some reasonable bounds for Kolmogorov distance in these kind of problems than I am with Wasserstein distance. So in general, for these Gaussian approximation problems, Wasserstein distance is easy in some sense, Kolmogorov distance is hard in some sense, because of the difference in the smoothness of those underlying functions h. So mostly I'm going to think about in these notes in these lectures, thinking about Wasserstein Wasserstein distance because that's easier, and it gets us away from sort of technicalities which I don't want to have to spend too much time thinking about because I want to concentrate on some other points instead. So I'm mostly going to think about Wasserstein distance where I have smooth functions h because that's easier. There are at least a couple of different solutions to the fact that that if I want to approximate in Kolmogorov distance that my functions aren't smooth. One solution is to use results like this that say that essentially once I've got a bound once I've got an upper bound in Wasserstein distance, I can immediately turn that into a bound in Kolmogorov distance. So I just take the square root of the bound that I get and multiply by constant 2. So I can use the fact that a bound in Wasserstein distance does imply an upper bound in Kolmogorov distance as well. But that's definitely not ideal because the order of this bound is typically not correct. This square root that we get here is essentially costs us in terms of the rate of convergence that we get. So if I just want to show that this upper bound is finite or something, sorry, somehow if I want to, if it's always going to be finite, it's always the most one. But if I want to show that it's sort of well behaved in a very loose sense, then results like that might help. If I want to actually prove correct rates of convergence, optimal rates of convergence, then these kind of results are not particularly useful, unfortunately. But they certainly are results like that there. And I give you a proof which I'm not proposing to say anything about. But if you want to sort of see how that's proved, then there's a proof there. It essentially you replace the h that we replace the indicator function by a version that interpolates linearly in some way, which gives me a smooth function that I can work with, and then use the fact that we know some bounds on the distribution function of my Gaussian random variable. So I'm not going into details because it's a sort of step away from what I really want to talk about right now, but we can do that. A better solution, though it's certainly more work in general, which I'm also not actually going to talk about, but if I think I don't even put a reference, but I can give you a reference for these kind of arguments. So I could replace in my Stein's method argument, I can replace my indicator function h by a smoothed version. So essentially it depends on some continuous smoothing parameter, which I'm going to let tend to 0 eventually. Once I've got that nice smooth function of that indicator function, then I can do exactly what I want with that because that's now differentiable. But then I just have to be very careful about how I'm letting that smoothing parameter tend to 0. Well, I just need to handle those limits carefully. I need to make sure that I'm doing that in a correct sort of way.
So we have a question or a comment in the chat.
Yep.
And Nikolai comments, it seems the term Kantorovich distance more preferable than the Wasserstein distance. So Kantorovich considered the problem. So Kantorovich considered his problem earlier. Do you know anything about it? Okay.
So I thought might be true. I think it probably is true. Yes. I've inherited my terminology from lots of the literature, and I think so. I've seen this called the Kantorovich distance. I've seen it called Wasserstein. I've seen it called Wasserstein-Kantorovich. As with many things, this has several names, and I'm. But yes.
So basically, it's the same. Yes.
Yes, I think so. Yes.
Okay. Okay. Because for me, the Wasserstein distance is also more. I'm used to Wasserstein distance rather than Kantorovich too.
Yeah, I don't know the history as well as I probably should. I have no idea who thought about this first, but it's certainly plausible that it wasn't Wasserstein. Yeah, that's
okay.
But yeah, I think the terminology is interchangeable. I think you're right.
Okay, thank you for your comment.
Thanks. No, yes, thank you. Okay, so I think that was what I wanted to say about those proofs. So I'm not going to go into details about how to work with the smoothed with these smooth versions. It's mildly more complicated. It's not absolutely terrible, but it's a little bit more complicated. Okay, so what I want to spend probably the rest of today on, I think, yeah, this is thinking about how we can take the proof that we just had and relax the assumption of independence. Okay, so I'm going to, well, we want to think about perhaps what we could, some sensible options that we could replace independence with and still use essentially the same argument that we just did. So this is one approach. I'll mention others, but probably not till next week now, about how to establish explicit BAMs. But certainly one approach is to essentially take the argument that we just had and relax the independence assumption, so be a little bit more careful in the couple of places where we used independence. So let me just remind you where those places were. So I used independence to get rid of when I was looking at WF of W, I had the first term in my Taylor expansion, and when I took expectations, independence allowed me to set that to 0. And I also, at some point, used independence around here when I was looking at F prime of W. So we're going to, let's think about how we can relax that independence assumption, but use essentially the same argument. Okay, so the argument isn't really going to change very much. So there are a number of ways that I can relax this independence assumption, which sort of fall under the heading of what you might think of as local dependence. Local dependence meaning, roughly speaking, that for each, so I'm still thinking about a sum of random variables. So W is still a sum of my x's, and over some index set that we might as well think of as the numbers 1 to n, but we can be a little bit more arbitrary if we want to. So I have n of these random variables. Local dependence essentially means that each one of these depends strongly, in some sense, only on a small subset of the others, and the dependence between the dependence outside that subset is somehow weak, or perhaps even they're independent. Each of these x's is independent of everything apart from a small number of the others. So there are a number of ways that we can make that kind of assumption more precise. And so the first and perhaps most obvious way of making an assumption like that is to do exactly what we just said and say each xi will depend on a small subset of the other x's independent of the rest. Somehow we'd think of the ones that it's dependent on as being maybe close to it in space or in time, however we're thinking about, whatever situation we're thinking about, whatever sort of model we have. Somehow each xi is dependent on things that are close to it, but independent of things that are further away. Okay? Is one way of making this sort of local dependence assumption. And we can prove results under that assumption. That's actually not quite what I'm going to do. I'm going to allow ourselves to be a little bit more flexible in that, in the particular local dependence assumption that I want to make has essentially the same flavor, but let's just allow ourselves a little bit more flexibility. In that I'm saying, so for each of my xi's, so the subset of my other x's that xi is dependent on, and it's going to be independent of everything else, and all of those, so what do I mean by x? With a set as a subscript, I mean the collection of all of the x's whose indices belong to that set. So the collection of all of my x's within there. So all of my x's outside the set of things which are independent of xi is independent of a whole bunch of other x's. So this takes a little bit of thinking about. but it's essentially one way of sort of formalizing this, this sort of idea of local dependence. So,
can you maybe draw it like the sets to give some sense? Because, well,
yeah,
like with circles or something like that.
So what's the easiest way to think about this? So for each I, so I've got my random variable xi. I've got, okay, so I've got all of these other x's. I've got some subset of those that it's kind of, I have some
Yes.
So I've got some subset which this depends on. So this is my collection of kind of xai. So this set here is my collection of sort of xai, which is somehow close to my xi, and which xi depends on.
Mm-hmm.
And then we're independent of everything else in here. So everything that's kind of out here, so this is my collection of xai complement, and I'm going to assume that, so we're assuming xi is independent of everything out here. So this collection of random variables here is independent of xi. And I don't know whether I want to complicate that diagram by drawing more things on it, but then there's some, have I got? Let me just check that this red pen works. Give me 1 second just to find another color.
Okay.
It's going to get better. It's going to get. So then this collection of xai's depends on some xbi's. So then there's this collection of this collection, if I can show this in a slightly different way, even this collection. So then there's some xbi's which live out, so this ai is a subset of bi, and my and everything in. I maybe won't draw this on the picture because it's going to get complicated, but then everything essentially outside, everything in this sort of set, on the picture, is everything outside there is independent of the green things. So everything, these xai's, this bit in the middle, is then independent of this sort of outer layer of things. So these sort of, we're allowing ourselves to sort of think about this sort of almost two distance kind of problem. So things which are close are dependent on the thing I started with, and then as I get, then these things which were dependent on the xi I started with, then have their own sort of neighborhood of dependence living around them, things which are close to them, but then they're independent of things which are further away.
Okay.
So is that okay? Does that make sense?
Yeah, it's much clearer. Yeah, sure.
The picture was a good idea, thank you. So this is now my xbi complement, which is independent of my xai's.
Mm-hmm.
You sort of,
yeah.
we get a picture like that for each I.
Yeah.
So I've picked a particular I, but just like we did in the proof for the independent case, we're going to have we're going to look at each I separately.
Mm-hmm. Thanks.
So if we do that, so again, I'm assuming each of my x's are normalized to have mean 0, and that the sum has variance 1, so same normalization. We'll end up with a bit more of a complicated bound, not surprisingly, that will depend on the sum of the x's within this within this blue set, so the sum of my x's that depend on I, and the sum of my x's which live in this outer set, this green set, and so the sum of those x's which depend on the xai's, and we'll end up with a somewhat more complicated bound, but things we can deal with in the sense that what I've got, so each of these terms is just a sum of my x's. So we at least are just going to end up with products of x's. So nothing worse than third moments essentially, or maybe some fourth moments come in there. But no, it's essentially still a third moment type bound, which is not awful. So it's the same sort of flavor as what we had in the independent case, even if the bound, of course, is a bit worse, as you'd expect it to be, because we're allowing ourselves a lot more to be a lot more relaxed about independence. So now, what I want to use is essentially exactly the same argument. So I'm going to, at some point, exploit the fact that xi is independent of all of my x's. So there's a sum of all of my x's, take away the ones that it happens to be dependent on. Okay, so I've constructed this sum so that xi and w minus this eta I are independent. So given that that's true and these x's have mean 0, then I can do something very similar to expectation of w, f of w, as I did in the first in my independent case. So I just write that as the sum of, write this w as the sum of my x's, and then all I'm going to do is take away this xi times, or the expectation of xi times f of w minus eta I. That expectation is 0 because w minus eta I and xi are independent, and x's have mean 0. So that gives me a way of writing my wf of w. So that's what I had before, and now I'm just adding and subtracting this eta I times f prime of w. It's just another way of writing the same thing. And that gives me a representation of my wf of w, where essentially the active terms, the interesting terms are now have some f primes, and the rest is, okay, it's not 0 anymore when I take expectations, but we can deal with that in a bit. But essentially it's the same kind of argument where I have essentially some kind of Taylor expansion, which lets me write my wf of w's in terms of f primes. So I'm aware this argument takes a bit more digesting. It does get significantly more complicated, but it's not. But I guess what I want to emphasize is that the fundamental idea of the argument is the same as the independent case. Okay, there's some more technicalities to worry about. We have to be a little bit more careful. We have to worry a little bit more. But the fundamental idea of the argument is the same, and we don't need to change the approach. We just need to be a little bit more careful about how we're actually using this argument. And again, when I want to handle my f prime term, I can use the fact that I've normalized so that the expected value of my w squared is 1. I can write that in terms of the underlying random variables. Again, using the fact that xi is independent of anything outside this blue set, my ai's. And that allows me to get some representation for this expectation of w, sorry, f prime of w minus wf of w that I want to bound. So there's my f primed of w, and there's my f prime of w, and that's the other term there came from, combined with that was my representation for my wf of w. So far I've sort of exploited the fact that each xi is independent of anything outside this blue set AI. And now we can go a little bit further. We can also exploit the fact that these x's in this blue set AI are independent of everything in this outer red set that we drew, to use essentially the same kind of argument to be able to take away some zeros by looking at W minus the sum of everything apart from those red things. So everything apart, that's it. Yeah. Yes. And so again, we can exploit independence exploit this independence result that anything within this blue inner set is independent of everything in this red outer set. We get a similar kind of representation, and then I again just want to apply Taylor's theorem to each of these two terms to be able to get things in terms of second derivatives. So this first term I can again bound in terms of second derivatives of f. So I can take Taylor expansions of this f prime of w around w minus tor I. We'll get we've got some things in the front that I want to take care of, but essentially I'll get an f double prime times these things. I can use a similar sort of Taylor expansion on the second term as well, and that way, so I can again write that. I can again bound that using a triangle inequality in terms of the second derivatives of f, and that's good because now I know how to control those second derivatives. I'm working Wasserstein distance, so my underlying h's are differentiable, so I can apply the lemma that we had an hour or so ago, and that tells me how this second derivative behaves, which then gives me my explicit bound. So I'm aware that there are a lot of details there that I went very quickly over, which I tried to avoid doing earlier on, but I think these are details that you, in some sense, do need to go away and read relatively carefully. But what I want to give you a sense of is that the argument is essentially the same as the independent case, and we just have to be a little bit more careful about how we're applying, how we're working with our representations. But the argument is essentially exactly the same. The one last thing I want to say today, because I'm aware that we'll deal with that example later on. But the one last thing I want to say today is just that if I happen to be independent, then of course I can apply this result. What I'm going to do is take AI and BI just to be I itself. So the only things that xi depends on are itself, and that's everything else is independent. So that's good. Note this. If I do that, I get essentially the same result as we had in the independent case, just with a slightly worse constant. I get a 5 instead of a 4. But as I say, that 4 was not a particularly good constant anyway. So 5 is essentially an equally bad constant. So we don't really lose anything if we specialize our local dependence result to the independent case. We don't lose very much at all. A slightly worse constant, but slightly worse for a constant that was already not that great. So did anyone have were there any other questions or comments before I sort of?
Yes, here's a comment in the chat. Again, Nikolai asks you, could you recommend papers to start working with the global dependence, maybe with mixing conditions?
With mixing conditions. So off the top of my head, no. Look, can I think about that and get back to you? Is it? I can look at that in the next couple of days if that's all right. I can pick out some references. Off the top of my head, I can't think of references for using mixing conditions in this setting. But if I can get back to you on that, then that would.
Yeah, I think it's fine.
Is that okay? If I can postpone that question to think about it a little bit and probably give a better answer than I can now. But yeah, that's a good question.
Anyway, in the last lemma, so I guess we sort of secluded the point I, make a set AI, then set BI just by doing basically making balls out of every point in AI also. We somehow make a bad situation of a bad situation, I guess. But I don't know. I mean, I guess it's a silly question, but if you go further and go from BI, take every point that also dependent and make a CI, which is even bigger, can you make anything better here? Maybe with additional derivatives or something? I don't know.
Maybe, yeah. So there's a whole host of local dependence assumptions, and yeah, some of them. This is in some sense a two-step approach. You can get bound under a sort of one-step local dependence. So where there's just AIs and no BIs, you could do something similar with some CIs as well. Would it get you anything better? Perhaps. So I guess the advantage would be that you can then sort of allow the dependence to get a bit weaker further out. So you sort of get closer to allowing your XI to depend on everything in some sense.
Okay.
So yeah, so you definitely could derive a result under that in that kind of setting, and whether it would get you anything better for simple examples, probably not. But you might be able to construct examples where that does give you something better. Yeah, I mean, not necessarily in terms of derivatives, but just in terms of say constants that you'll get or something like that.
Okay.
I think for this kind of argument, second derivative is probably the right thing. So second derivatives of f's are probably the right thing to end up with, and I think taking higher order Taylor expansions doesn't necessarily win you anything.
Okay.
But you might be able to do better with constants, perhaps. I expect you to get the same. If for reasonable problems, I'd expect to get the same sort of rate of convergence, because I expect that you're doing sort of the right thing anyway. But you might be able to get better constants.
But then again, better constants is not really about Stein method.
Yeah. So there's
I guess.
Yes, yeah. I mean, so in some sense, and you want to use Stein's method to get some explicit error bounds, and those explicit error bounds include constants, which you perhaps want to plug into your problem to check, well, what is a sensible upper bound? What explicit upper bound can I calculate on the Wasserstein distance between W and Z?
Okay.
But the constants you get are not necessarily going to be great, so that upper bound isn't necessarily close to the true Wasserstein distance, even if it's got the right order.
Okay.
So there's certainly some limitations there, but yeah.
Oh, and I guess just another question. Just can you just quickly say an example of a model where this non-trivial dependency where it just goes with Bloom or whatever?
Yes. So if I just written there that I decided I ran out of time to. I always love questions where you just scroll onto the next slide and the answer's there.
Nice.
So we can think about examples like this, where I'll go fairly quickly because I'm aware that I'm kind of running over. But suppose so I've got some graph with a whole bunch of vertices. I'm looking at local max. Yeah. So I'm looking at, so on each vertex I've got a set of IID random variables, one for each vertex. Assume they're continuous, so that we can assume they all have different values. And I'll say that vertex I is a local maximum if the random variable that lives there is bigger than the random variables for any other vertex that vertex I is connected to. So these are this NIs are the vertices for which the vertex I is connected to by an edge. I'm a local maximum if I'm bigger than anything that lives in that neighborhood. So one statistic you might be interested in is how many local maxima are there on this graph. So how many vertices are there for which which are bigger than anything they neighbor onto, or whose random variables are bigger than anything that they neighbor onto, anything they're connected to.
Okay.
It's not too hard to get the mean and the variance of those things, and it's also, you can sort of convince yourself that these things should be asymptotically Gaussian, because in some sense it's a sum of weakly dependent things. I just sum over all my vertices, and these things somehow are, that they're certainly not independent, but they're not that dependent either. And I can take, if I want to, so the AI, so the things that these indicators that tell me whether or not I'm a local maximum at vertex I, what do they depend on? Well, they just depend on things which are at most 2 edges away. So essentially the neighborhood of my neighborhood, because anything further than that doesn't actually affect whether I'm, it doesn't affect whether I'm a local maximum at vertex I or not, but things closer than that do. So obviously the values, so if I know that, so vertex I and vertex j are connected, and I know that vertex j is a local maximum, that tells me I isn't. But also somehow if I need to go one step further as well, because neighbors of j, once I know about those give me some information about whether I think my random variable at vertex j is large or small, and that tells me what I think of it. That gives me some information about vertex I as well. So I need to sort of think about this neighborhood being everything that's distance, so the number of edges at most 2 away from the thing I'm interested in. And then my B's are just everything that's 2 away from everything that's 2 away from I. So that's everything that's 4 steps away from I at most. So there's one example where you get this kind of setting.
Thank you.
And there's actually nothing more to that example, because I deliberately didn't do the calculating the upper bound. I just wanted to show you exactly what your question was, which is, here's a setting where you can do this. So there's actually everything that's there.
Okay.
Are there any questions? If not, maybe we should thank Fraser for a good introduction. I think it was all clear, at least for me.
I'll start next week by asking if you've got any questions on what we've done just now anyway. If I forget to do that, then please remind me, but I'm happy,
Sure.
happy to go back on.
We can't see you, Sergei Georgievich, because you have your camera turned off.
So okay, I try to applaud, to do it. How does it work? It's okay. It's noisy.
Thank you.
Okay. It's bad that there is no real feedback. I'm sorry. So it's when you see audience, it's much better. What to do?
Yes, yeah, it's
okay. Thank you, Fraser.
I think turning off cameras is a good idea for everyone's internet connection. Mine especially, since I'm running my phone and my desktop off this internet connection. So yes, it's certainly much nicer. I would much rather have come in person and seen everyone face to face and be able to chat a little better and more easily. Yeah, as you say, what to do.
Maybe it will become better next time or further on, because, well, yeah.
Anyway, thank you very much.
Thank you.
Thank you.
Thank you.
Thank you.
So
Okay.
see you next week.
Yes.
Yes.
Yeah. I'll see you next week.
Goodbye.
Yeah.
I'll send you an email with the link and stuff.
Sounds perfect. Thank you very much.
Thanks.
Okay.
Thank you everyone who participated today.
Fraser, talk tomorrow, yeah?
Yes, yeah, sounds good. At 10 o'clock, I think we said. Is that the UK time?
Fine, thank you.
Perfect. Thanks. Bye. Bye.